Welcome to Chem 1A at Shasta College. This is Chapter 3, Composition of Substances and Solutions, Screencast number 2. And we're going to start with an example where we have a sample of a compound that's been analyzed and it's found to contain 0.1313 grams of nitrogen and 0.3749 grams of oxygen. And we're going to find out the moles of nitrogen and the moles of oxygen in this sample of compound, as well as the number of nitrogen atoms and the number of oxygen atoms in this sample of compound. We'll also find the formula of the compound, the formula mass, and the molar mass of the compound. And let's do these bit by bit, starting with moles of nitrogen and oxygen. And as we've seen already, if we know the grams of an element, we can look up its atomic mass, and for nitrogen it's about 14 grams in 1 mole. And by using the appropriate conversion factor, we can then convert from grams of nitrogen into moles of nitrogen, and in this case we get 0.009367 moles of nitrogen in this sample of compound. For oxygen we do the same thing, except we use the mass of oxygen in the compound and the mass of oxygen per mole, which again is found on the periodic table. And since 1 mole of oxygen is about 16 grams, we can convert from grams of oxygen into moles of oxygen. And in this case, we get about 0.02343 moles of oxygen in the compound. Next, we'd like to find how many nitrogen and oxygen atoms are in this sample of compound. And what we do is, to get number of atoms, we're going to start with moles. We have 0.009367 moles of nitrogen. And what we know is that 1 mole of nitrogen, like 1 mole of anything, consists of 6.022 times 10 to the 23rd particles. And in this case, the particles are nitrogen atoms. That's our conversion factor, converting from moles of nitrogen into atoms of nitrogen, and we get 5.641 times 10 to the 21st nitrogen atoms. We use the same process for oxygen, except we use the moles of oxygen. Same number of particles per mole, 6.022 times 10 to the 23rd oxygen atoms in 1 mole of oxygen. That's the conversion factor that lets us convert from moles into atoms for oxygen, and we get 1.411 times 10 to the 22nd oxygen atoms. Now, what's the formula for this nitrogen-oxygen compound? And note, we can use either moles or atoms and the ratio of those to get the formula for the compound. That's the key idea. The ratio of atoms of nitrogen to atoms of oxygen, or the ratio of moles of nitrogen to moles of oxygen, is going to be the same as the ratio in the formula. So if we use oxygen to nitrogen moles, 0.02343 moles of oxygen, generally speaking, I like to divide the bigger number by the smaller number. You don't have to, but I find it a little easier to see the ratio, what it works out to be. So divide by 0.009367 moles of nitrogen, and when you divide that out, you get 2.501. And now we have a little interpretation to do, and we note that 2.501 as a ratio is 2.501 to 1, and specifically it's moles of oxygen to moles of nitrogen. So we basically have 2.5 moles of oxygen per 1 mole of nitrogen. And then what you need to do is recognize that a 2.5 to 1 ratio is the same as a 5 to 2 ratio. And remember that chemical formulas are small whole number ratios of the elements involved. So once we know our small whole number ratio, then we can get our formula, which is there are 2 nitrogens per 5 oxygens, and so it's N2O5 is our formula. And of course, we could have done this with atoms. And again, my preference is divide the bigger number by the smaller number. So 1.411 times 10 to the 22nd oxygen atoms divided by 5.641 times 10 to the 21st nitrogen atoms, we get 2.501, same thing as before. And this is, of course, a ratio now of oxygen to nitrogen atoms, and a 2.5 to 1 ratio of oxygen to nitrogen atoms is a 5 to 2 ratio of oxygen to nitrogen atoms, and that small whole number ratio gives us the compound's formula, and it's N2O5. We get the same thing if we do an atom ratio as if we did a mole ratio. Now next we would like to find the formula mass for this compound, which has an empirical formula of N2O5 we just found. And it's probably worth noting here that we found the empirical formula, we found the smallest whole number ratio of nitrogen to oxygen, and to find the molecular formula we would need to have additional information. Specifically, we'd need the molar mass or a mass spectrum or something like that. And in this case, I'll just simply tell you that it turns out that the compound we just analyzed, the molecular formula is the same as the empirical formula. So the substance is dinitrogen pentoxide N2O5. And its formula mass is the mass of one molecule of the formula unit of N2O5, which is 2 times the atomic mass or the mass of nitrogen, which is 14.1 AMU atomic mass units, and then 5 oxygens is 5 times 16 atomic mass units. That adds up to 108.02 atomic mass units. So one molecule of dinitrogen pentoxide has a mass of 108.02 AMU, and that's the formula mass. Now the molar mass is the mass of 1 mole of this compound, and it turns out that the molar mass will give us the same number, but different units as the formula mass. And specifically, for every 1 mole of N2O5, there are 2 moles of nitrogen. Each mole of nitrogen weighs 14.01 grams, so that times 2 is the amount of, or the mass of nitrogen in this compound. And then each mole of N2O5 contains 5 moles of oxygen, so 5 times the mass of oxygen per 1 mole, which is 16 grams, add up to 108.02 grams, and that is the mass of 1 mole of dinitrogen pentoxide. And we normally state the molar mass as a grams per mole value, so we would say the molar mass of N2O5 is 108.02 grams per mole. Note that in general, the mass in grams of 1 mole of any substance is what's called its molar mass. So we have the compound iron 3 chloride, molar mass of 270 grams per mole, copper sulfate 249.7 grams per mole, and similarly potassium iodide, sodium chloride, potassium manganate with the 7 oxidation state for the manganese ion, and then cobalt 2 nitrate. Molar masses of these substances are shown, and the amount of stuff that makes 1 mole shown in the picture. And that's it for screencast number 2.